So we want to discuss about directional derivative and the gradient vector. So recall the partial derivative was basically rate of change in the direction of coordinate axis. So namely partial derivative with respect to x at say AB, at a point AB was change rate of change in direction of x-axis because you kept y constant, right? So, or we can say in direction of, but the direction of x-axis is same as that is in direction of unit vector I. Yeah, I'm just putting a cap on it to emphasize on the unit vectorness of it. Similarly, you had partial derivative of y with respect partial derivative of f with respect to y at AB was rate of change in direction of y-axis or in direction of the unit vector j. Now, there's no reason why we cannot compute the rate of change in arbitrary direction. So for that, the concept of directional derivative comes into the picture. So suppose we have a point here, P on the curve. So suppose we have a point P, which is given by say P x naught, y naught, z naught. Yeah, and this is basically z equals to f of xy is your function. So now you go on to the projection of this point. Say you are at P prime x naught, y naught, 0. So projection onto xy plane will look like that. Now, instead of going in this direction, in that case, you got the partial derivative with respect to y, or instead of going in the direction of x-axis, we will now take an arbitrary direction. So what we are going to do is this is our point P x naught y naught 0, and we'll take any other point here, and we want to go in this direction. So let u be the direction here. So this direction is u. It's a unit vector, u, and we will look at the following. So this point is going to be, suppose this point is q prime. We have x, y, 0. This corresponds to, let me draw the plane containing if you look at this plane here, it will cut your surface like that. And on top of this point, we have q, x, y, z. So we want to see how much that the function changes in the direction of u, which is on top of the curve. How much is the rate of change of function along this curve? Okay. So let's figure that out. So in this case, we have vector p prime q prime is in the direction of u. So let's call this, it's some multiple of u. So it's going to be h u. Okay. So u is a unit vector. I should write that down. Unit vector. Now, suppose on top of that, we have suppose we have u equals to vector A, vector B. Then what is the change of your function in this direction? So from this point to this point, the change in the function would be essentially, so this point is, so you have, this point is x naught, y naught, p prime is x naught, y naught, 0. And what is our q prime? So q prime is, I will have coordinates x naught plus h, y naught plus h, 0. And correspondingly on this curve, then we'll get the change in z would be delta z, and that would be vector length, vector p will have, how much did it change? It will change from this point P to Q. So it should be f of, sorry, it should be AH, right? Because what do I have is HA, HU. So HU is H times A, H times B. So what is the change in the function I get is f of x naught HA, y naught HB minus f of x naught, y naught, and then divided by h, would basically divided by h. And this will be the change from P to Q, okay? So this is the average change. And then when you take limit as h goes to 0 of delta z over h is the rate of change of f in direction of vector u, which will be taking limit of this guy. So it makes sense to talk about this object as the directional derivative of your function. So we get the following. So directional derivative of f at x naught, y naught in the direction of u is given by, so we need a notation to capture that, because you had this represented, if you looked at the xf, it was partial derivative with respect to x. So we want a representative, a notation for directional derivative of function at a point x naught, y naught in the direction of vector u. And that is given by, the notation is du f of x naught, y naught. And it is the same limit we found out on the top. We have x naught plus HA, y naught plus HB minus f of x naught, y naught divided by h. So this is the directional derivative of your function f at x naught, y naught, but in what direction? In the direction of unit vector u. Yeah. So now let's go back a bit. Say, what does it captures? So in some sense, say, let's say take a point here, take a point P somewhere here. Then one can ask the following question. Standing in this point P, in which direction is the ascent is steepest, all right? Or I should say, because my P is here, I should say which direction is in which direction is the descent steepest. So if I'm coming from down here, say somewhere around this point, so which direction should I go up to have the steepest ascent, right? So this basically measure. So directional derivative measures that, right? Because directional derivative will see what is the rate of change in that direction. And these are the contour lines which basically tell you what is the height at that point, right? So when you're talking about the descent, it makes sense to talk about it because you don't want to take this, the path of the, the steepest descent, right? You'll be toast, right? I mean, you'll be on the other side of the cliff, right? So that's the idea behind the directional derivative. So it's a very meaningful object because it captures the rate of change in certain direction, because there's no reason why we should restrict ourselves to the rate of change in x, in the direction of x axis, or in the direction of I, or in direction of j. Okay. So notice that if you look at this problem, then you'll see that if you take unit vector I, then essentially you're looking at limit as h goes to 0 of f of x naught plus h, comma, y naught minus f of x naught y naught over h. Yeah, why is that? Because the reason for that is that I is your unit vector 1, 0. So this is essentially partial derivative of this with respect to x, so of your function evaluated at x naught, y naught. So you see the directional derivative captures this information. Similarly, if you look at partial derivative in the direction, so directional derivative in the direction of vector j is going to be partial derivative with respect to y at x naught, y naught. Okay. So this is what the definition of definition of directional derivative is. But then the next question is, how do we compute such an object? Yeah, because computing the partial derivative with respect to x and partial derivative with respect to y was easy in the sense that you kept one variable constant and you differentiated with respect to the other variable. So what about the directional derivative? Is there a way to make this computation easy for us? And the answer is yes. So the answer is, if you have a direct differentiable function, f is your differentiable function of x and y, and if it has directional derivative in the direction of any unit vector u, which is AB, then du of x naught, so du, the directional derivative in direction of u at x naught, y naught is partial derivative with respect to x at that point times a plus partial derivative with respect to y times b. Now, if you look at this theorem, it's actually, it's very interesting that again, we are back to computing the partial derivative with respect to x and partial derivative with respect to y. So if we compute these two objects, we are good to go, right? So we just need to compute this two guys and we are good to go. So we'll define a new object called a gradient vector to capture fx and fy. So what is a gradient vector? So gradient vector. So consider again f a function of two variables, x and y. Then the gradient of f is a vector grad f defined by what? Grad f is simply the first component is partial derivative of f with respect to x. Second component is partial derivative of this with respect to y. So gradient is itself a function, right? It's a vector function, all right? So similarly, we can define gradient at a point x naught, y naught. That would be simply substituting instead of x and y, you're substituting for x naught, and for y, you're substituting y naught. So in this sense, you are evaluating your function at x naught, y naught. So the directional derivative of f at x naught, y naught in the direction of u is therefore given by what? So you had directional derivative of f along u was given by this, and you can rephrase it as fx x naught y naught comma fy x naught y naught dot with vector AB. Yeah, so you can write it as what? You can write it as the first one is a grad, so grad of f at x naught y naught dot with the unit vector u, which is AB here. Okay, so this is what the directional derivative is. So it's meaningful to actually see a very quick proof of this. So let's see a quick proof of this. So why is that the case, right? So why is this the case? So notice the following. So let me write down the proof of this. So we have, first of all, we have du of f is essentially, say at x naught, y naught, is limit as h goes to 0, f of x naught plus ha y naught plus hb minus f of x naught y naught divided by h. So now consider the function g of h. So we'll make a one variable function out of this. So our one variable function will be a function of h. So g of h, let's take this to be f of x naught plus ha y naught plus hb. Yeah, that is my g of x. So now note that, so this implies g of h minus g of 0 over h, which is g prime at 0, is exactly equal to your partial derivative, sorry, directional derivative in the direction of u. Yeah, do you agree with that? Because just take g of h. G of h is this part here. What is g of 0? G of 0 is taking h and h0 in both of these, which is going to be f of x naught y naught, and then divided by h. So this object and these two objects are same. So you see that g du of f of x naught y naught is your g prime of 0. So why did we do this? Because g prime of 0 is easy to compute. Why is that? Let's compute g prime of h. Now note that it's a function of one variable. So it's going to be, so what is, this is going to be respect to x times dx by dh plus partial derivative of this with respect to y times dy by dh. Yeah. Now, what is the reason for this? Because your z, your g, which is a function, g can be thought of as a function of x. These are function of h. So what do we get? What is a partial derivative of this with respect to is going to be, what is dx by dh? Dx by dh, x is this guy. What is the derivative of this with respect to h? Is simply going to be a. What is the derivative of this guy, which is your y, with respect to h? Is going to be, so first part as it is, dy by dh is going to be b. So now you can see that y you get yeah. And of course, these are evaluated at what point? These are evaluated at, so this is evaluated at x naught, y naught. This is evaluated at x naught, y naught. I want to make that clear. So this is the setup, right? So now we should be able to compute. Let's do the following problem. Now we know how to compute it based on the partial derivatives. So let's compute now. So given f is this, find a gradient vector of f, find the directional derivative of f at 2, 1 in the direction of vector v. So suppose you have f of x y equals to x squared minus y squared. So find the gradient of f. So gradient is a function, all right? So gradient of f is partial derivative with respect to x is the first term, partial derivative with respect to y, the second term. So this is going to be partial derivative with respect to x for the first term is going to be 2x, partial derivative with respect to y for this guy is going to be minus 2y. So this is your gradient. Now directional derivative at 2, 1 is going to be what? The directional derivative at 2, 1 is going to be du, sorry, we have v. So our vector is v, but note that v is not a unit vector. So let's say first we need to find out. So u unit vector along v is take the vector 1, 1, divide by its length of vector 1, 1. Now length of vector 1, 1 is 1 square plus 1 square square root, which is square root of 2. So it's going to be 1 by square root of 2, 1 by square root of 2. So therefore, what do we get? We get directional derivative of this guy at 2, 1 in the direction of v. The notation is going to be of f at 2, 1. By definition, this is going to be grad of f evaluated at 2, 1 dot product with this unit vector, which is 1 by root 2, 1 by root 2. And that is same as, so what is the evaluation? So first one, it will give me 4, and the second one will give me minus 2 dot with 1 by root 2, 1 by root 2. And this is going to be 4 minus 2, which is 2 over root 2. Okay, so this is the directional derivative in the direction of u. So this is the partial derivative. So this is the partial derivative of f at 2, 1 in the direction of u. All right. So now whatever we did now, there is no reason why we cannot generalize it to 2 variables, sorry, to 3 variables, 4 variables, or n variables for that matter. Okay. So we'll come back to this in a minute. So we'll generalize this to function of 2 variables and to function of 3 variables in a moment. But let's understand the geometry of the gradient first. So what does grad f does? So grad f points in the direction of the steepest descent, right? And the grad f is orthogonal to any level curve of f. So these are the two important aspects of the geometry of the level curve. So why is that? Let's see. So suppose f is a differentiable function of 2 or 3 variables. So we'll generalize this into 2, 3 variables in a moment. The maximum value of the directional derivative du of f of x is going to be grad f of x. Now, why is that? Notice the following. So we have is going to be grad f evaluated at, say, so suppose this point was, let me write down the components so that things are clearer. X naught, y naught is simply grad of f times vector u. So this is a dot product of these two things, which is going to be length of grad length of u cos theta. But this guy is a unit vector. U is a unit vector. So we get not y naught cos theta. So now when you look at this, one thing becomes clear, that what is the maximum value of the directional derivative. So you have length of this times cos theta. This is maximum when cos theta is 1, right? So, and when does maximum appears? Maximum appears when theta is 0. That means that is same as saying what u is of same direction, or rather using same, we should say parallel to grad. Yeah, so in vector setup, these two vectors are parallel, right? These are anti-parallel. Okay, so this is anti-parallel, right? So the arrows should also head in the same direction, right? Anti-parallel. So now, because of this analysis, you can see the following. So this theorem now makes sense, that the maximum value of the directional derivative is going to be the length of grad f, and it occurs in the same direction as direction of grad of f of x naught y naught. That means u has the same direction as the gradient vector. Okay, so this gives you the maximum change, or in other words, you can think about this as what? The steepest change, right? The steepest change, if you're going up, it's an ascent. If you're going down, it's a descent, right? So for example, if you have level curves like this, then what you're doing is you're looking at the points where what you get? You get that the level curves are perpendicular to this path, and you get the steepest ascent. If you're going from low to down, or if you're going from 300, level curve 300 down to 100, then it will be steepest descent. So let's talk about directional derivative and gradient in R3. So the same story can be generalized. We have gradient of vector valued function of 3 variables. So let W be f of x, y, z. Then grad f is going to be fx, fy, fz, which is written in the IJK format. And the directional derivative can be defined in the same way. You have f of x naught plus ha, y naught plus hb, z naught plus hc, minus f of x naught, y naught, z naught divided by h, limit as h goes to 0. Provided, of course, this limit exists. If it doesn't exist, then the directional derivative does not exist. And this is the notation in the vector format. So this is the key for computing the directional derivative. So again, in some sense, we generalized the idea of partial derivatives with respect to x and y, but then we are saying, hey, partial derivatives are still in the game because you can compute the directional derivative using the partial derivatives. So let's take the following function. So let f be x e to the x z plus yz. Find the gradient of f. Find direction derivative of f at 1, 1, 0, and in the direction of vector v. So let's embark on this problem. So we have, first of all, we'll compute the gradient. So what is my gradient of f? So first one is partial derivative with respect to x. So let me just write down. So we get so partial derivative with respect to x is going to be e to the z. For the first one, partial derivative with respect to y is going to be just z plus x e to the. So let me just write that down here. So it's going to be, the first term is going to be x e to the z, plus from the second one, when you take derivative, you get z. And then the partial derivative with respect to z is going to be, hold on a second, I'm doing partial derivative with respect to y. So when I do partial derivative with respect to y, I'm computing, this will become 0. I'm simply going to get z. And then when I do partial derivative with respect to z, this is what I get. I get x is a constant, comes out, derivative of e to the z is e to the z, and plus derivative of yz with respect to z is going to be y. So now find, this is the gradient. So find directional derivative at 1, 0. So this is going to be f at evaluated at 1, 1, 0. Again, I need to find out what my unit vector u is going to be 1, 2, 1 divided by length of 1, 2, minus 1. So what is the length of this? So 1 square plus 2 square plus 2 square. So that is going to be square root of 6. So this is going to be 1. I can directly write this to be v over square root of 6. Yeah, that is my unit vector. So this is going to be grad f evaluated at 1, 1, 0 dot with vector v over square root of 6. So this is going to be, now I'll substitute 1, 1, 0. So when I substitute 0, so I get 1. When I substitute 0 here, I get 0. When I substitute 1 here, so I get 1 plus 1, which is 2, dot with vector v, which is 1, 2, minus 1 divided by square root of 6. So this is going to be 1 minus 2, so minus 1 by square root of 6. So this is my directional derivative in the direction of vector v. All right, so now we want to talk about the tangent plane to the level surface. So what is a level surface? So note that it's a level surface is you take f of x, y, z and equate it to k. So then you get what is called as level surface. So let's draw a level surface and look at the tangent to that. So we have the following. So let's take a surface. Okay, so let's this be your surface here. All right, so now we'll choose a point at which we'll try to draw a tangent plane. Okay, so this be my surface S. So I have Z equals to f of x, y. Actually, that is not correct. It is given by rather f of x, y, f of x, y, z equals to k, because it's a level surface, right? Now, we have a point here, P, and so the idea is, so if you take a point P, then the perpendicular then to this surface is given by grad f x naught, y naught, z naught. So it makes sense to talk about a tangent plane to the level surface. The definition makes sense to be what? to have a plane for which this vector is the normal vector. So this is what the tangent plane to the level surface would mean. Okay, so this is a new definition. So new definition. So this is a new definition of tangent plane to a level surface. So what is the tangent plane to the level surface? So this is a level surface. You're looking at the tangent plane. The tangent plane is a plane which passes through x naught, y naught, and z naught, and has normal as x naught, y naught, has normal as grad f evaluated at that point. So if you look at that, so it will look like quite like this. And this is the normal to that tangent plane. Okay. So now the question is, how do you find the equation? Well, you already have the normal, right? So if you already have the normal to the, this is your n. So you get x minus x naught. So if you recall the vector equation, you had x minus x naught, comma y minus y naught, z minus z naught times grad of f of x naught, y naught, z naught equals to 0 is the equation of the tangent plane to the level surface. So you see that this is what we get after we simplify. Okay. But question, does it has any connection with the original definition of the tangent plane? Yeah, so we have to reconcile these two definitions. We can't have two definitions of tangent plane hanging around, right? So how about we reconcile this definition with the known definition of tangent plane to the surface? So for that, consider the following level surface. So you have, so your z equals to f of xy can be written as f of xy minus z equals to 0. So consider this as your function f of x, y, z as your level surface. So this is your level surface. And now what does our equation tells us? Our new definition is, what do? You basically take fx at x naught, y naught, z naught times x minus x naught plus fy x naught, y naught, z naught, y minus y naught plus fz x naught, y naught, z naught at z minus z naught equals to 0. So this is your definition, right? So let's see, what is fx? Fx is going to be partial derivative of f with respect to x, right? And that will be evaluated at x naught, y naught, because there's no slot for z naught. So x minus x naught. Similarly, this is going to be partial derivative of this with respect to y. So first one will be fx y, x naught, y naught, and then z naught. Z is constant with respect to y now, because you're looking at the level surface. In level surface, your x, y, and z are three variables, right? So we get y minus y naught. And then what do we get here? Plus fz. Fz is going to be what? The derivative of this with respect to z is going to be simply minus 1. So we get, this becomes minus 1 times z minus z naught equals to 0. If you bring this on the other side, you get your usual tangent plane for the z equals to f of xy. So you see, these two definitions are actually the same definitions in disguise. Yeah, the only difference is when you're talking about level surfaces, you're not talking z as a function of f of xy. Let's look at this example for here instant, right? So here z is not a function of xy. Why? Because it fails. You can think about it as failing a vertical line test. We can have an analogous definition of vertical line test for this guy. Or another way to look at that is that for one value of xy, there are two values of what? There are two values of z. That is not a definition. So at best, this is a level surface. But the question is, can we still find out the equation of the tangent plane? And the answer is yes. So in some sense, this new definition is a generalization from the previous one. So again, let's find this out and then we'll be done with the discussion. So we have my f x, y, z is going to be x squared plus y squared minus z squared equals to 1. Yeah. So then what does it tells me? The equation is going to be, what is the equation of tangent plane at this point is going to be fx at 1, 1, 1 times x minus 1, fy at 1, 1, 1, x y minus 1 plus fz at 1, 1, 1 times z minus 1 equals to 0. So let's see, what is fx? Fx is 2x, fy is 2y, fz is minus 2z. So therefore, when we substitute in, we get 2 times x minus 1 plus 2 times y minus 1 minus 2 times z minus 1 equals to 0. So this is the equation of your tangent plane to the hyperboloid at 1, 1, 1.